Okay, so basically this whole chapter for chemistry is experimental chemistry. So at the end of the lesson, you need to know how to be familiar with all your lab equipment, especially all the glassware, okay, the things that you can measure. Then we also talk about gas collection methods and gas drying methods, and finally separation techniques. So very briefly, okay. So measurement, we can measure things like mass. Okay, so mass we measure using this electronic balance you see in lab. I think nowadays in lab should all be digital already. So all you need to do is just read the number over there, or then make sure you get the units correct. So okay. Then we can also measure length, although not very common in chemistry lab. Okay, as you know me. And there is time. So time sometimes you want to measure like, oh, how long does it take for your reaction to produce maybe 50 cm of gas? Okay, then we use stopwatch. Okay, so this one what you see here is another stopwatch. Okay, we have digital ones also. Okay, and then we can measure things like temperature, very common one, or temperature. Okay, so temperature, we sometimes when reactions occur, either your reaction solution will get hotter or colder. Then you can use this one to monitor how hot, how cold it is. Okay, so got two types of thermometers. Okay, you should be familiar with two types. Okay, one is the mercury thermometer. So mercury thermometer is like a piece of glass where inside there is mercury, and this liquid inside is mercury. Okay, that will expand when it's hot, and then it's contract when it's cold. Then basically it will move up and down. Then you just okay, a bit laggy. The voice is laggy or the visuals is laggy or both. Voice. Is it clear enough? No, is it I'm supposed to speak very near the is this okay, then maybe I bring my on this one. Okay, like that better. Okay, okay, it is still laggy, you let me know again. Okay. Okay. So going back to thermometer, okay, first type is mercury thermometer. Okay, so mercury inside just read the readings. The other one is digital thermometer, which I think someone told me that actually they use a slightly different one in school. Okay, the school one, right, will look like this. There's like this plastic thing over here with a screen. It is not very maybe it's 27 degrees Celsius. Okay, then there's a metal, like this probe, metal here. Yeah. So all you need to do, right, is let's say you have a solution, you just dip the middle part inside the solution, then the reading will come out already. So this one is like, um more convenient, I guess. Yeah. Okay, so got two types. This is digital, so yeah. Then you can measure things like volume also. So volume, okay, for measurement of gas, right? Only got one option, which is the gas range. Look at that one. I think this one is very largely magnified. Right? That by right is very small. Okay, the problem, right, the difficult part for this part is to choose the apparatus to measure volumes of liquids correctly. Yeah. Okay, so you have the burette pipette. Okay. So burette basically this one is one that can measure very accurate, okay, up to 50 cm cube only. Because that's the maximum volume of the burette. Okay. Then I think I wrote this down in the notes before. Basically it looks like this. This is 27, then you have a line to separate it like that. So it can go down to like 6.1, 6.2, etc. Okay. Then for pipette, this one is accurately, but only one volume. So depends on the size of the pipette also. The ones that is most common inside the chemistry lab now is this one, 25 cm cube. So other than the 25 cm cube, it cannot measure any other volume. Only got one volume. Then you fill up the list line already, right? And that's it already. That's 25. I won't know where is the 24, where is the 23, etc. Only one volume probably. Okay, then we have the beaker. So beaker usually, I think I mentioned before in the lesson also, this one we do not use this for measurement. Usually this one is because it's a large container. Okay, it's used more to like contain all the reaction mixtures. Then let it react there. Okay. We are at every one of setting. Hello, hi Natalie. And I just verify you are Natalie Fo, right? Correct. Because I see the name spelled slightly differently. Okay. Okay. So currently I'm just going through the notes I recap. Those earlier part that you have missed out, maybe if you want you can watch the recording. Okay. Okay, so volume measurement, okay, you can use measuring cylinder also. This one, okay, usually up to 0.1, depending on the size of the measuring cylinder also. Uh, then lastly is volumetric flux, which is just measure one volume, but it's a large volume instead of a small volume. Okay. Okay. Okay, then this one very simple. The TLDR, right, is basically your liquids, right? Sometimes inside a container is not a straight line. It has a curve like that or like that. Then how to read, right? Basically, you go and find the middle part of the curve, then you read one. So for example, this one, you want to read this level here, this one. Okay, then over here, we want to read the middle, this one. Uh, okay. So water usually appears there on the downward curve. Then we talk about collection of gases. So there are four ways to collect gases. Okay, very quickly, upward delivery means the gas is going upwards like that. Okay, and then I want to collect the gas here. So the gas must be less dense than air so that it can float and it doesn't drop out like doesn't come out. So things like hydrogen and helium will float. Then with upward delivery means we also have downward delivery. I want to collect the gas here, the gas current here. Okay, so this one is to collect gases that are denser than air. Okay, so they don't fly up, they don't fly up when they escape when they're gone already. So things like carbon dioxide, you carbon dioxide, chlorine, and sulfur dioxide. Okay, then there is one which is water displacement. Okay, so water displacement basically is this whole thing originally all filled with water, then I bubble the gas into it. So then the gas will be collected inside here instead. So then it will like that. Okay, so this one only is suitable for gases that are insoluble in water. Okay, if they can dissolve in water, then you try and bubble through water, it will dissolve, then gone already, you cannot collect also. Okay, so not suitable for ammonia. Okay, if you all want, right, you can write down another one. Another one that is not suitable is hydrogen chloride. Hydrogen chloride. Okay, this is HCl. This also cannot use it also. It's also very soluble in water. And then last one, of course, is pump the gas directly into a gas fridge. So this method is the best. Okay, because I don't care whether the gas is less dense than air, more dense than air, or whether soluble in water or not. Okay, just directly pump into a gas fridge and can even measure the volume. So this one is a measure gas fridge. Okay, then also cover a bit about drying of gases. So basically, we want to try and remove the moisture content, which is all the water vapor inside the gases. Okay, because if not, then it wouldn't be a pure sample of gases. Okay, in order to dry the gas. So we have three options here, one, two, and three. Okay, so first option for you to use will be calcium chloride. So one, this one also. It is a chemical formula. So calcium chloride, you can use this to dry most gases. You cannot use this to dry ammonia. Cannot. Okay. Then the other one is concentrated sulfuric acid. This is a solution. Okay. All gases total also except for alkaline gases because if it's alkaline, right, then this acid will react with the alkaline gases to remove it, and then we got no more already. Okay, so things like ammonia. This ammonia got a lot of problem. Okay, this one is alkaline gas. So method one, method two cannot. Means method three, right, must be for the alkaline gas really lot. Right? Okay, so calcium oxide, this is a method Ca with oxygen, CaO. Okay, so this one stable acid to acetic gas, because this one is a base, or stable base. So base cannot use to collect your acetic gases, like sulfur dioxide, all this kind. You'll keep out of it. Hope she coming back soon. Okay, then we move on to separation techniques. Okay, so separation techniques basically the first idea to highlight to you is that there's this concept of pure versus impure substances. Okay, so pure substances confirm you cannot split anything out in terms of separation. Like a pure water, how do you separate one water molecule from another? Cannot okay. So pure substances only made up of one substance, whereas impure is a mixture of two or more. Okay, like air equivalents and sure. Okay, so just let you know, okay, your pure substances melt and boil at fixed temperature. This is important. Okay. Then impure substances, they don't have fixed melting point or boiling point. You cannot say like, oh, a mixture of salt water, this one is boiled at 107 degrees. It's usually over a range. So it's from 103 to 109 your boil. Okay. And then the effect of impurities, basically it will lower your melting point and increase your boiling point. So if let's say I have salt water versus pure water, I know the melting point is 0, and then my boiling point is 100. So if let's say I added salt inside, then it becomes pure already. Yeah, hello, hi. Okay, I continue with the recap first. Those that can miss out, you can watch the recording. Okay. Mhm. Okay, so if let's say I have salt water, then melting point will be slightly lower than 0, so we get -3. Yes, -3. Okay, then boiling point maybe 140 degrees, so it seems to be high. Um, Okay, then separation technique, right? Basically, the whole idea of separation technique you need to be very familiar. Okay, the choice of the method, right, depends on the physical property differences. So one must be able to do something, whereas the other substance inside the mixture cannot do something. Then you can use that one to your advantage and then you separate these two uh, compounds or components. Okay, so as I think the first part of the lesson we covered like the separation between two solids. Okay. So two solids we can use maybe magnetic expression as the difference in the physical property. So one must be able to be one is magnetic, one is non-magnetic. Uh, so if one can be attracted, then you can use a magnet. For example, iron findings in cell. Okay, so this one will be attracted, this one not attracted. Then I just put a magnet there, then all the iron findings will come out. Okay. Yeah. Okay, second one is sieving. This one based on particle size. Okay, so C is like, okay, also draw is symbol settings. So it only allows the smaller particles or the finer particles to pass through. Okay, then the larger ones will be on top of that is on it. All the larger ones will drop off. Only the small one will go through. Okay, so this one, the physical difference is particle size. Then we have suitable solvents. So this one is, for example, your salt and sand. Okay, so salt and sand, one soluble in water, which is a salt. This one not soluble in water. So if I add water, the water will dissolve the salt, but then the sand will still remain as a solid. Then later I can remove the sand out via this method called filtration. Yeah. This one later we'll go through filtration. Because this one right, is separate liquid and solid. It's a solid. Okay, so this one difference in solidity. Yeah. So you have to choose the correct solvent. Then lastly is sublimation, which honestly not very commonly seen, especially in O-level, etc. But it's good for you all to know too. Okay, so sublime is basically the process where something converts to gas from solid directly. So it skips the liquid phase. Don't have liquid phase. Okay. Then basically what you do is you heat the mixture up. Okay. This thing cannot sublime, whereas the ammonium chloride has sublime. So this one cannot. So when I heat it up, then after that, only the ammonium chloride will convert to gas. So you see this one over here is all the gaseous ammonium chloride, like the vapor. Okay, then when it touches the surface on top here, it's colder because here don't have heat already. Then it will cool down and then convert back to solid directly. So totally no liquid phase. It will convert back to solid. So that's how I separate off. This one will come out. The one that cannot, slime will stay from here. I look like draw very fuse. I think will be good for you all to know also what are the solids that can slime, the common ones. Okay, so dry ice is one definitely you all need to know. Okay, solid carbon dioxide. Oh, that's very, very famous. Okay, and the other one is iodine. Okay, for iodine, you all will see this more in the next